chi-square test for independence or chi-square test for no association, critical value approach. Now, before we begin, let's just reflect a little bit on that symbol chi. It's a Greek symbol, and the English counterpart is ch, which is the symbol to represent chu. So if you need to spell a word that's starting with chu in English, you use ch, a word like change, for example, or church, okay, or choose. So why that symbol chu? Well, if you take a look at the formula for the chi-square test statistic, you can see there is a subtraction in the numerator and it is squared. And O minus E, that will give you the observed subtract the expected. That's like calculating a difference. That's calculating a change, okay, from the observed to what is expected. All right, so it could be that's where this symbol originated from, because you actually trying to test whether or not there was a change from what was expected to what was observed. Nickname, you can call it the change squared test. In words, change is the same as difference, which is equal to observed subtract expected. Symbolically, chi is symbol O minus E, and therefore the change square is equal to chi square, which is O minus E all squared. So could be that's where the symbol originated from and gave it the name chi square test. And because you're basically testing whether there was a change starting with ch, and the Greek counterpart for ch was used, and it gave the name, that's where it what is namesake, right? Could be, all right, because that's what this test is about, testing whether there was a change from what you expected to what you are observing. Here we're going to discuss the chi-square test for independence or no association. A researcher was interested in analyzing whether or not there was an association between major and performance in mathematics, for example. For this objective, the data is represented in the following table. So the topic could be major and academic performance in mathematics, all right? And as you know, following any topic in a research project, you have a research question, which could be here: is there an association between major and academic performance in mathematics? That's a legitimate research question. Okay, that's what a researcher is asking. Is there an association between major and academic performance in mathematics? Okay. Now, to investigate whether or not there is an association between major and academic performance in mathematics, it could be that a test was given amongst the natural sciences and the social sciences, and this table is depicting the results. So according to this table, 61 students from the natural sciences scored less than 60%, and 89 students from the social sciences scored less than 60%. And 99 students from the natural sciences scored more than or equal to 60%, and 81 students from the social sciences scored more than or equal to 60%. And the information said to use the chi-square critical value of 3.841, because a critical value approach. Now, every research question has possible answers, okay, called hypotheses. All right. So if a question is asked, is there an association between major and academic performance in mathematics? Step number one, a possible answer is that there is no association between academic performance and major. And another person could answer, well, there is an association between major and mathematics performance, yes? And the one that is saying no association is called HO, and the one that is saying there is an association is called HA, because the name of the test is for no association. So the HO, which is the status quo, will be saying no association or independent of each other. Okay, that's what the HO will be saying, that major and mathematics performance or mathematics score are independent from each other. While the HA, the alternative, will be saying that there's a dependency. So the test has to be performed so that the research question can be properly answered, which hypothesis or which answer is the correct one, according to the data that was shown. So since we are taking a critical value approach, the critical region has to be identified. And for a chi-square test, the critical region is on the right side of a skew to the right curve. Yes, and the critical value is placed on the critical point, 3.841. 0 is in the beginning of the number line, and this will take care of step 2, 3, and 4 in a chi-square test for independence using the critical value approach. So here's the critical region identified. Okay, so we move on to step number 5. Step number 5, we have to calculate the chi-square test statistic. Here's the formula. We introduced to it already. It is the sum of O minus E all squared divided by E. The values that are in the table are the values that was observed after the test was given. It was observed that 61 students scored less than 60%. It was observed that 89 students scored less than 60% from the social sciences. It was observed that 99 students from the natural sciences scored more than or equal to 60%. It was observed that 81 students from the social sciences scored more than or equal to 60%. But what was expected, because basically that test trying to compare what you observe to what you expected. So the expected value now is calculated using this formula, the row total times the column total divided by the grand total. You must find the totals of the columns first by adding the observed values. 61 plus 89 will give us 150. 99 plus 81 will give us 180. And you have to calculate the row totals. 61 plus 99 will give us 160. 89 plus 81 will give us 170. And then the grand total will be the addition of the subtotals. 160 plus 170 will give us 330. 150 plus 180 will give us 330. And with those values, we can calculate the expected values. So it's the row total for 61. Each observed value will have their own respective expected value, because each one will have a distinctive combination of row total and column total. Although they may share the same row total, like 61 and 99 have the same row total, but they have different columns totals. Okay, the grand total will be used for all. So you have, for example, 61, you have 160, that's the row total, times 150, which is the column total, divided by the grand total, 330, to give us 72.73. 99, the row total is the same 160, but the column total is 180, grand total is 330. 160 times 180 divided by 330 will give us 87.27. 89, 170 is the row total, column total is 150, grand total is 330. 170 times 150 divided by 330 will give us 77.27. And 81, the row total is 170, but the column total is 180. 170 times 180 divided by 330 will give us 92.73. So now we have the observed values and the expected values. We are going to compare them with this formula, O minus E all squared divided by E. And this was done using Excel. So you have a column of the observed, a column of the expected values, and the formula O minus E all squared divided by E. 61 minus 72.73 all squared divided by 72.73 to give us 1.89. And this was done for all the others, 99, 87, 89, 77.27, and 81 and 92.73. And these were added because the formula is to find the sum. So these are the chi-square contributions, 4 of them, and the chi-square contributions were added to give you the chi-square test statistic, which is 7.73. Now, step number 6, now we have to represent this chi-square test statistic on the distribution curve using the critical value as a guide. This diagram is not drawn to scale, but it is not necessary. We all just want to know where the test statistic is going to land. If it's in the unshaded region, that's the non-critical region, or the shaded region, the critical region, using the critical value like a boundary, if you will. Okay, so as you can see, 6.73 is more than 3.841. So therefore now, here is the logical place on this number line to represent the chi-square test statistic. And as you can clearly see, it is in the rejection region. It is in the critical region. The test statistic is in the critical region. Okay, so when I say it is in the critical region, I mean the test statistic of 6.73 is in the critical region. So we move on to step number 7. So since the test statistic is in the critical region or the rejection region, the decision is to reject the null hypothesis, because the null hypothesis is rejected whenever the test statistic is in the rejection region. If the test statistic was not in the rejection region, then the null hypothesis would not have been rejected. Okay, but since the test statistic is in the rejection region, the null hypothesis has to be rejected, because either you reject the null or you do not reject the null. Always bear that in mind. Okay, so as you can see clearly here, this hypothesis was rejected, which was the null. So since the null was rejected, then the alternative will be the conclusion. You will always begin the test with 2 hypotheses. One will be the conclusion. Okay, so in step number 8, since the null hypothesis was rejected, then the alternative is the conclusion, and we have to quote for our conclusion what the alternative is saying. So therefore, based on the data that was observed, there is an association between major and academic performance in mathematics, because that's what the alternative is saying. There is an association. Okay, so based on the data, okay, based on the values that were observed after performing the the test, then it appears that there is an association between your major and your performance in mathematics academically. So here's an example of a chi-square test for independence using the critical value approach.